there's a lot of different algorithms that you could use to search for a path in a graph. Okay, well, what are some of them? Let's talk about them. I'll show 4. I may not get to all 4 of them today, but I'll try to get to as many of them as I can. The first one I'm going to show you is called a depth-first search, DFS. So here goes. Again, in terms of the general topic of path searching, there's lots of different things you might want to optimize. You might say, well, I want to know the least expensive path. This is a pretend airline ticket map or graph here where I can get from Honolulu to San Francisco for a $130 plane ticket. And of course, these flights probably have a flight time and distance as well that isn't reflected in the graph. So you might want to find a path from Honolulu to Miami that minimizes the number of hops. Hey, there's a direct flight from Honolulu to Miami that costs $500. Sign me up. Sleep on the plane. But maybe if I'm willing to hop 2 or 3 times, maybe the end cost is a little cheaper. Maybe that's the thing I care about the most. I'm willing to have layovers as long as I can save a few bucks, etc., right? Or maybe I don't care. It depends on the application. Maybe all I want to know is, can I get to Miami somehow from Honolulu? Is there any path that will get me there? Sometimes that's all you care about. So you might choose a different algorithm searching for the path depending on what you're trying to optimize, if anything. Okay? So one algorithm that you can use to search for paths is called a depth-first search. And these names are supposed to give you an intuition about how the algorithm works. When I say depth first, I mean this algorithm performs deep searches. And so what I mean by that is you explore looking for paths. So you're going from a starting vertex to an ending vertex. And what you do is you explore possible paths as far as you can before you try another possible path. Guess what we're going to go back and do a lot of this time? We're going to do a lot of recursion and backtracking now. Yay! But hey, I mean, these topics are not meant to be isolated from each other, so backtracking is useful here. The idea would be, if I want to find a path in this particular example from A to F or A to I or something like that, well, maybe there's different ways I could go, right? So why don't I try one and just follow that as far as it leads me and see if that gets me to the destination of I. If it does, there's my path. If it doesn't, I'll sort of unchoose, I'll backtrack, and I'll try a different option. And I'll keep trying all the different options until I find one that works. The first one that works, that's my path. That's depth-first search. Okay? So what would a depth-first search from A to H do in this graph? Thanks. A depth-first search from A to H, the first path it would try would be, well, I'm assuming that if you say, like, for each neighbor, visit the neighbor, so maybe those come out in alphabetical order. So the first one I try is A to B. Then from there, I try everywhere I can go from there. I go to E. From there, I try everywhere I can go from there. F, I can go from F to C. Then I get stuck. Why does that have a... There's some kind of I there on the graph. Oh, there's an I see. From C, you can get to I. Sorry, I didn't really see this. I should make that curved or something. There's a line from C to I. That's as far as you can go down that path. I can't get to H, so I unravel and I backtrack basically all the way back to A, because there were no other splits. There were no other ways I could go from any of those. I guess C gets me to E, but I already went that way. It was already visited. So basically, I backtrack all the way back to A, and then I try some other option. I don't try E, because I already got to E through B. The idea is sometimes with these algorithms, as you reach a vertex and you're searching, you sort of check it off as being visited. You mark them. And as you mark a vertex, if you ever get back to that place again, you know that you've already been there before, so you probably don't want to search that place again. It's not useful. So I'm not going to try the path starting from A to E, because I already got there previously going through B. Okay? So I don't go this way, but I try the A to D path. That leads me to G. It leads me to H. I guess the way that this algorithm would have worked is it would go A to D, and then just try the first alphabetical neighbor of D, which is G, and then the first alphabetical neighbor of G, which is H. You might say, wait, stupid, you could go this way, A, D, H, that's better. Well, I'm just telling you that's what this algorithm would do. This algorithm, as you might see, doesn't always produce the shortest possible path. It just finds a path. It has the virtue of being one of the easier path-searching algorithms to code. So if you consider that a perk, this one has that perk. Let me ask you, just in terms of reviewing and make sure we're on the same page, let me ask you a Socratic question about DFS, and let's see if we can figure that out. So let me pop up a Socratic question now. Here's the pseudocode for DFS. It's a recursive function. From V1 to V2, mark that vertex is visited. If it's a destination, stop. Otherwise, for each neighbor that hasn't been visited, call recursively on that. So what path would I find from A to F in the graph there? Take a look. Feel free to talk to your buddy if you want to. Let's look what you folks are voting on. Looks like most of you picked choice D, which I think is the right answer. We're assuming that the vertexes get visited in ABC order. So I hope you understand that this algorithm would choose A, B, E, F, because the first path it tries is B. From B it tries E. From E it tries F. And so it would find that rather than the shorter path, A, E, F, the direct path, right? Or A, D, H, F. There's nothing wrong with A, D, H, F. It's just that we would find one on our B exploration, so we would never get to checking D. So that's why the algorithm would find answer D instead of answer B. Okay? So yeah, that's DFS. Now, one thing about DFS that comes up is, usually when you run these algorithms, you want to know what the path is that the algorithm found, right? If you look at this pseudocode, I say, hey, if you're going from V1 to itself, then the path is found, hooray. But what is the path? How do I actually know what the path should be? This pseudocode doesn't address that issue, right? If you were writing this as code, how do you think you would know what the path is? Like if you had to print out the path or return the path or something like that as a vector of vertexes. Any thoughts? What would you do?
Just pass a vector around the recursive function by reference.
Sure.
Like choose and unchoose.
Yes, that's a great idea. He said pass around a vector by reference, keeping track of the vertexes I've chosen. This is basically just a recursive backtracking algorithm. Choose every neighbor, explore to see if I find a path, unchoose if it doesn't work out. So what we do with a lot of our recursive backtracking algorithms is we pass along a collection or something as a helper to remember what we've chosen, right? That's what we've done in all of our backtracking examples. So just like pass along some kind of, I called it path in the pseudocode, but maybe that's a vector for the path or a set or some kind of a collection. You probably want it to be ordered like vector so that it'll keep track of the order that you visited the things. Basically, every time you visit a vertex, add it to your vector, and if you ever get to the end, your vector is the path. But if you ever backtrack and say, nope, I didn't find a way to reach the destination, then you unchoose by removing yourself from that vector, right? This is the basic idea of a choose, explore, unchoose recursive backtracking solution to DFS that will have the path for you when it's done, if it finds one, okay? There we go. So that's DFS. Any questions about that algorithm so far? Yeah.
Are you keeping that question with it, like the related parameter?
Oh, that's a great question. I have a couple of magic mumbo-jumbo phrases on these slides that if you're actually thinking code here, you have to have a way to translate those into C++. Like I say, mark these vertexes as being visited. And what does that mean? Like, how do I mark a vertex? I mean, conceptually, you could imagine if we're just doodling pictures that, oh, I visited you, okay, I visited you, I visited you, right? Like, but we don't get to do that in the computer. We have to have an analog for that in our C++ code. There are a lot of ways you could do it. One way would be maybe you could keep some kind of set of vertexes you visited and add vertexes and remove them from the set, pass that around as a parameter to your function. You could do that, or a map, or something like that. It turns out that by the design of our basic graph library, it actually kind of helps you with that. Let me see if I can show you that real quick here. the slides from last time. A jump to near the end of this. So we haven't talked about this too much yet, but stored inside of each vertex of a basic graph is like this little vertex structure. It has a Boolean field inside of it called visited. So you can actually go get the status information for that vertex and just set its visited field to true. And so actually the basic graph facilitates this by letting you just mark the vertexes with a Boolean. So that aspect of the pseudocodes that I'm showing you, you'll be able to map pretty much one-to-one to a line in your C++ code. Okay? Anyway, back to the new slide. So that's DFS. I don't know, do I have anything else to say about that algorithm? I guess what I'd say is it will find, if there is a path, it'll find one. It's not guaranteed to find the best one. It'll just find some path. It could find literally the crappiest path in the whole graph. But hey, that's what it's for. It finds a path. It's pretty easy, if you find the path, it's pretty easy to have it and emit what the path was through your little vector that you pass along. Not optimal path. Okay. Let's do another one. Let's do one called breadth first search, BFF. So if depth first search explores deeply, breadth first search explores broadly and shallow. So, I mean, keep in mind, like, why do we say this is depth first? Because when A goes and tries exploring B, it explores all of the things that could come after B before it ever backtracks to try going down from A to D or something like that. You understand? So it does a deep exploration of things that could follow B before it tries anything else.